Hey everyone, welcome. Ready to dive into some seriously mysterious stuff. So we're going to break it all down. What they are, how they form, all that good stuff.
The stuff that'll impress your friends, like, hey, did you know about black holes?
Uh-huh, exactly. But you know what's really wild? Our journey actually starts way back in the 18th century.
Oh, yeah, way before we even dreamed of going to space ourselves.
Right. Like no rockets, no telescopes like we have now.
But even then, scientists were already thinking about, like, what if there were these supermassive stars?
Stars so massive that nothing, not even light, could escape their pull.
Exactly, they called them dark stars. Jean Michel, Pierre-Simon Laplace, those guys were ahead of their time.
It's incredible when you think about it. But it wasn't until Einstein, right? He's the one who really cracked the code.
Absolutely. Einstein, 1915, theory of general relativity, changed the game completely.
General relativity. That's where it all clicks into place, right?
It is. See, Einstein said gravity isn't some, like, mystical force. It's all about how massive objects warp space-time.
Whoa, okay, slow down a sec. Warp space-time. Mind blown.
Think of it like, imagine a bowling ball on a trampoline.
Okay, I'm picturing it.
That bowling ball makes the trampoline sag, right? Anything that gets too close is going to roll towards it.
Right, because the bowling ball is changing the shape of the trampoline itself.
Exactly. It's the same basic idea with black holes and space-time. They warp the fabric of the universe, creating this intense gravitational pull.
Okay, I think I'm starting to get it. But how did we go from, whoa, space-time is warped, to, yep, black holes are real?
That's where Cygnus X1 comes in.
Cygnus X1. That rings a bell. Wasn't that some kind of big discovery?
Huge. In 1964, astronomers found this incredibly dense object emitting powerful X-rays.
X-rays. Okay, so, like, how did they connect that to black holes?
Well, they observed how the matter around this object was behaving, spiraling inwards, giving off those X-rays.
Sounds intense.
It was behaving exactly how we'd expect matter to act as it falls into a black hole. It was a major clue.
Like a cosmic fingerprint.
Pretty much. It solidified that black holes weren't just some theoretical idea, they were out there, for real.
That's amazing. But okay, what actually makes a black hole a black hole? I feel like we need to talk about escape velocity here.
You got it. Escape velocity is key. It's the speed you need to hit to overcome an object's gravity. Like, think about rockets launching into space.
We gotta go super fast to escape Earth's pull, right?
Exactly. The more massive the object, the higher the escape velocity.
Yo, black holes. Their escape velocity must be insane.
More than insane. It's faster than the speed of light itself, and since nothing can go faster than light,
Anything that gets too close is trapped forever.
capped forever. That's the point of no return, what we call the event horizon.
The event horizon, it's like a boundary, not a physical thing, right?
Yeah. Right. It's a boundary in space-time. And get this. Time itself actually slows down for objects approaching it.
Wait, seriously? Time slows down. Come on, that's like time travel
It's
stuff.
called gravitational time dilation. Mind-bending.
Yeah. Right. Okay, time travel later. Right now, I'm stuck on this whole trapped forever thing. What happens to all the stuff black holes suck in? Does it just vanish?
That's the million-dollar question, right? It's a puzzle that's been bugging physicists for ages. We call it the information loss paradox.
Information loss paradox. Okay, you're going to have to break that down for me.
So imagine a photograph, right? You tear it up into tiny pieces.
Yeah, heartbroken, but I'm with you.
Now, even though the photo's shredded, the information's still there. The people in the picture, the memory, it's all still kind of in those pieces, you know?
Theoretically, you could put it back together, right?
Right. And that's what quantum mechanics says about information in general can't be destroyed. But then we have black holes.
Which are like the ultimate shredding machines.
Exactly. And that's the paradox. What happens to all that information when something falls into a black hole? Does it just disappear?
That doesn't sound right. Doesn't really jibe with the whole information can't be destroyed thing.
Right. And here's where it gets even weirder. Stephen Hawking, he proposed this idea that black holes, they're not entirely black. They actually radiate a tiny bit of energy.
Hey, what? Black holes radiate.
Yeah, it's called Hawking radiation. Basically, because of some crazy quantum stuff happening at the event horizon, black holes actually lose a tiny bit of mass over time.
So black holes, they can evaporate.
In theory, yeah, over a ridiculously long time, but still.
But wouldn't that mean all the information they swallowed just vanishes? It doesn't sound right either.
And that's the heart of the information loss paradox. How do we make sense of this? We've got general relativity, which explains black holes, and quantum mechanics, which says information sticks around. They don't really agree.
So what are the options? How do we solve this thing?
Well, one thought is that the information isn't gone, it's just encoded in that Hawking radiation.
Encoded, like a secret message hidden in the black hole's energy.
Something like that, yeah. It's like the black hole is whispering its secrets as it evaporates.
Whoa.
Yeah.
Okay, can get behind that. Any other theories?
Another one is the holographic principle. This one says that information about a 3D object, like, say, a star that got too close to a black hole.
Uh-oh, the spaghetti star.
Exactly. So the holographic principle says that information about that star could be preserved on a 2D surface. Like, think of a hologram.
A 2D image that makes a 3D picture.
Right. So maybe black holes are kind of like projecting information onto their event horizons. It's a wild idea, but it could explain things.
Man, the more we learn about black holes, the weirder they get. But we still don't actually know for sure, do we? About the information, I mean.
Not yet. It's still one of the biggest mysteries in physics. And that's what makes it so exciting. It's pushing the boundaries of what we thought we knew about the universe.
It's wild to think that these things are out there,
Yeah.
like messing with our understanding of information itself.
And it goes even deeper than that, actually. When you start thinking about what happens to a black hole over, like, billions and billions of years.
You're talking about that whole evaporation thing again, right? With the Hawking radiation.
Yeah.
To be honest, that part always kind of tripped me up.
I get it. You think black hole, you think exists forever. But that Hawking radiation, that means even black holes eventually, well, they fade away.
So, no need to panic. They're not going to, suddenly disappear one day and take the universe with them.
Not a chance. We're talking about timescales way, way longer than the current age of the universe. It'd be like expecting a mountain range to just erode away in a day. It's a slow process.
Okay, good. Less apocalyptic than I pictured. But then, what's left? When a black hole totally evaporates, is it just gone? Empty space.
That's a question that takes us to the edge of what we know, really. Some theories say maybe there's a little something left behind, like a tiny point in space-time.
A point? With all that information, it ate up.
Potentially, but what that means, what it would even look like, that's still a mystery.
A cosmic ghost of a black hole. Okay, that's officially the coolest thing I've heard all day. But we've been talking about black holes like they're all the same. Are they?
Good point. Not all black holes are created equal. They come in different sizes, which just adds to the whole mystery, really.
So, what are the options?
The most common type you'll hear about, those are stellar mass black holes. They're born when a really, really big star.
Bigger than our sun.
Way bigger. When those stars die, they can collapse in on themselves and boom, black hole.
So all that mass crammed into a tiny space, that's what makes them so dense.
That's it. We're talking like several times the mass of our sun, but squeezed into an area the size of a city, maybe even smaller.
Okay, yeah, that's dense. Those are the small ones, right? What about the heavy hitters?
You're talking about supermassive black holes. These are the giants that live in the centers of galaxies.
Even our galaxy.
Yep. Right in the heart of the Milky Way, we've got one of these behemoths.
How big are we talking here?
Millions, even billions of times the mass of our sun. It's mind-boggling.
Billions? Seriously. How does something even get that big? Eating planets, stars, other black holes?
All of the above. We think they grow by gobbling up matter gas, stars, even other black holes over billions of years. And when galaxies collide,
Which happens.
more often than you'd think, when galaxies collide, their central black holes, they can merge. It's a cosmic dance-off, and the result is an even bigger black hole.
So they're constantly evolving. That's incredible. This whole deep dive has been amazing. Black holes are way more than just cosmic vacuum cleaners.
Right. They're these dynamic forces that shape the universe as we know it.
And the best part, we're just scratching the surface here.
Exactly. Every new discovery seems to raise more questions than answers, which is what makes it all so exciting, right?
Absolutely. So for everyone listening, keep those questions coming. Keep looking up at the stars and never lose that sense of awe and wonder. Until next time.